Alright, welcome to AP Video 10.2. This is the Properties of Liquids video. Main idea here is to continue using IMFs to describe the properties of solids and liquids. This one's mostly on liquids. And in this particular video, I'll be able to describe some properties of liquids like surface tension, capillary action, viscosity, volatility, vapor pressure, etc. Alright, so surface tension is the resistance of a liquid to increase its surface area. The particles in the interior of a liquid are attracted to other molecules within the liquid, and they're attracted in all directions, so the net pulling power, I guess, in direction this is going to go is nowhere. It likes to stay put because things kind of pull in all directions. But the surface, it gets pulled sideways, it gets pulled down like this, it gets pulled inward essentially. And surface tension is the resistance to increase that surface area. So try to pull these guys apart. It takes some energy to overcome that. And liquids that have high intermolecular forces, they have high surface tension. They don't like to get pulled apart. They like to keep this nice tight surface up here. Surface tension leads to a couple examples here, like you can float a paper clip on water if you do it right. This allows some insects to float on water, or allows them to stay on top of it. And also, we know that water likes to beat up. Okay, here's a little water droplet on a grass blade. So surface tension is why those things like to stay together. So kind of going with this idea of liking to stay together. A little ahead of myself here. I guess last we have a thing called a surfactant. Surfactants are other substances you can add to your liquids. And what surface tensions do, or surfactants do, is they reduce the surface tension. They essentially get in the way. So water is right here, it's IMFing together, and it likes to stay together. But over here, when the surfactant has been added, it basically gets in the way, and it doesn't allow water to create that surface tension, and it basically breaks that up. So adding a surfactant causes water to lose its surface tension, and things will fall through it. That bug would not be able to stay on top anymore, and so forth. Soaps and detergents are really good examples of surfactants. Okay, so back to kind of attracting to each other. That's actually a thing called cohesion. So the fact that water likes to cling to itself really well basically means the intermolecular force amongst its molecular particles, they like to stay together. So, think co-workers, cohesion. Co-workers work together. Cohesion is the IMFs clinging to themselves. Adhesion is kind of the opposite. The intermolecular forces of the liquid molecules like to attract to the container or something else. And those two forces are always kind of working together and kind of working against each other. Here's an example of water in a thin glass tube. You can see the water kind of lips up the side like this and creates what we call the meniscus. Water is clinging to the sides of the wall of the container and has more attraction for the walls of its container than does for itself. That's why it lips up. On the other hand, mercury here actually has a convex meniscus, goes like this, which means that it's attracting more inward to itself, and that's why it has that shape. So it has less attraction, or adhesion, for the walls, and has more cohesion for itself. So in this example here, cohesion is stronger than adhesion. And on this example here, we can see that the adhesion is stronger than the cohesion because it's going up the wall versus down the wall. Both these two things actually can work together for a thing called capillary action. Capillary action is when you have a thin enough tube. When you put some water near that thin tube, the water just kind of spontaneously goes up the tube. And what's really kind of happening here is water, I'll kind of expand the tube now. Basically what happens is water goes into this tube, it adheres to the wall, and then the water kind of rises up behind it like this. And then when the tube is narrow enough, what happens is it kind of adheres back, or has cohesion for itself, and it climbs a little higher, and then it adheres to the wall. And then it goes back and has cohesion to itself, and it kind of keeps going back and forth until eventually it gets high enough where gravity says, okay, you can't go any higher. But cohesion and adhesion work together for capillary action to take place, which is the spontaneous rising of a liquid in a narrow tube. Two places that this happens pretty commonly is in plants. They have the tissue called xylem. And a xylem vessel basically is a narrow tube that allows water to kind of go up like this. There's other factors that cause water to rise up into the plant, but the capillary action is one of the reasons. Another one is whenever you have to get your finger pricked and they're going to test your blood for proteins or other things, they prick your finger, and essentially this tube here, your blood will just spontaneously go into the tube. and then when you run out of blood, they'll squeeze your finger, get more blood out, and essentially it flows into this tube here. So capillary action is the reason for that spontaneous rising of liquid in a small tube. A couple other vocab words you need to make sure you know. Viscosity is a liquid's resistance to flow. Okay, so things that are more viscous are typically thicker, they don't flow as well. It's kind of like your idea of like maple syrup and oil, whereas water is a little more fluid. Viscosity is the opposite of being fluid. Volatility is the ease at which a liquid evaporates into a gas. Gasoline's a really good example here. Gasoline, as we all know, you pump in your car, it's a liquid, but you can definitely smell it, which means it's easily going to the vapor phase, and we can smell it. So volatility is how easily things can evaporate to a gas. And then lastly, we have vapor pressure. Vapor pressure is pretty unique. It's a closed system. Nothing comes in, nothing leaves. What happens is when you close your cap here, the pressure in here, we'll just say is 1 atm because it was atmospheric pressure. And once you cap it, the liquid particles begin to evaporate, and they begin to collect up in here in the chamber here. And as the gas particles collect up here, they also have the ability to go back down into solution. They recondense back into the liquid phase. But eventually, it's evaporating and condensing at the same rate, and the amount of new vapor up here becomes constant. The pressure that is due to that is called vapor pressure. And it only happens in a closed system because in a closed system, the particles cannot go anywhere, and then therefore they're going to re-evaporate. I think we all know if we took the lid off here, if the gas evaporates, it's going to leave this, and it's an open system, and it's not going to re-evaporate. So you're going to eventually just go dry here if you leave the cap off.